So, okay, number 14 says, a person places a cup of coffee on the roof of her car while she dashes back into the house for a forgotten item. When she returns to the car, she hops in and takes off with the coffee cup still on the roof. A, if the coefficient of static friction between the coffee cup and the roof of the car is 0.24, then what is the maximum acceleration the car can have without causing the cup to slide? Now, I gave you a shortcut for this yesterday. You guys remember the shortcut, or should we set up the free body diagram, or both?
We use the Greek. Is it Greek symbol?
Wait,
that's mu.
Yeah, that's mu for static friction.
Thanks.
Hold on a second, Stefano.
Can you please make the free body diagram?
We can make a free body diagram. All right. So the free body diagram for this. First off, the coffee cup has weight, and they don't give us the mass. We're assuming we know what planet it's on, so we know what gravity is. Okay? That's the first part. Now, if the coffee cup is not caving in the roof of the car, what else do we know is going on? And there's its weight. What is keeping the coffee cup from breaking through, Michael?
Normal force.
The normal force, which as long as the top of the car is level or close to it, is just going to be an equal and opposite vector straight up. Close enough for my purposes. So that will be mg, will be its magnitude, and that is the normal force. Okay, the car starts to accelerate. What is the coffee cup aware of?
Coffee cup might start shaking.
Itself in the roof, basically. It's not really aware of anything. But you know, we're anthropomorphizing
Here's a question, if I may.
Yeah. Okay.
Is it gonna slide or shake? I mean, depending on how you start. Like, if you just start like, it's gonna, of course, it's gonna go like that.
That's exactly what it means. How much acceleration will? That's what this question is basically asking. How much acceleration will cause it to just start to slide? Now, if you go way, whatever that number is, Daniel, if you go way over that number, it's going to just go flying off. Stay below that amount of acceleration, you should be fine. We're also discounting air resistance. We're not asking, I mean, if the day is windy enough, the cup's just going to blow off, right? So we're assuming there's no wind. We're assuming a lot of things. Okay, so the cup, being aware, air quote aware, of only itself in the roof, the cup suddenly feels this acceleration. And that is a force. That's the force the cup sort of feels as the car starts to accelerate. Okay? What's keeping the car? Why doesn't the car starts to move? Why doesn't the coffee cup just stay where it is because of inertia? And why doesn't the car just slide out from under it? What is the one-word answer?
Friction.
Friction. Excellent. Okay.
Sorry.
That friction is what keeps that from happening. Up to the moment when the car slides, these things are equal. The force of the car and the force of friction. The force of friction has to grow as the car accelerates, and at some point it'll be overcome. Okay? At the exact moment when this thing slides, these two vectors are the same. Split second, let's say before, let's phrase it that way. Right before the coffee cup starts to slide, this magnitude has to be equal and opposite to this magnitude.
They cancel each other out.
Yeah.
Because the exact coefficient of friction.
Yes, the coefficient of friction helps tell you when that happens. That is the percentage of the coffee cup's mass. This is like saying 24% of the weight of the coffee cup can be used to prevent it from sliding. But that's it. That's the only amount of its weight that can be used. Luke looks like he has a question.
Are these problems in our book?
No, this is a worksheet I put up last night.
Oh, okay.
I didn't put up to like 5 p.m. though, or 4:30, so you may not have.
No, I didn't, but I was curious because I was looking at the answers.
All right, no, they're not. Yeah, no, these don't line up with the ones in our textbook. Okay, so shortcut is I know the force due to friction is going to have the same magnitude as the
mu times mass times gravity.
well, it's the coefficient of static friction times the normal force times mg, right?
Yeah.
Okay. Now, this force that the car is pulling, this is a mass times an acceleration, right? But as far as the coffee cup's concerned, it's its mass. the force that the coffee cups feel is not the force of the entire car. It's just the force of its mass times the acceleration it feels. It's all the force it needs to be dragged along. Does the car need its entire mass to make this coffee cup move? No. And besides, this free body diagram is only about the forces exerted on the coffee cup. So this force down here, this purple one, this is the mass of the coffee cup times the acceleration caused by the car. And these two things will be equal at the moment the cup starts to slide. What can I divide out from both sides of this equation?
Mass.
Mass, yeah. So do I have to care about the mass of the coffee cup?
Yeah, wait.
Do I, in order to solve this problem, do I have to care about the mass of the coffee cup?
No.
No. And in fact, the coefficient of static friction is just going to be equal to, what was that? How does this question phrased? What's the maximum acceleration?
Yeah,
Okay.
it's the.
Yes.
So the maximum acceleration is the coefficient of static friction times g.
Which would be 2.4
2.3
meters per second squared.
Sounds about right, because it's going to be 0.24 times 9.8 meters per second squared.
Yeah, it's practically
Kind of
10.
like multiplying by 10.
Yeah.
Kind of.
So it doesn't round to 2.4?
So maybe it'd be like
Yeah.
2.3.
2.352, but that is 2.4.
Because it's two sig figs, right?
Yeah.
Okay, so this is going to be, you can accelerate at 2.4 meters per second squared. Before I answer Michael's question, just going to say real quick, you can think of this coefficient of friction two ways. You can think of it as the amount of your weight that you use to resist acceleration before something starts to slide. You can also think of it as the percentage of 1g that will cause you to start to slide. So if you have another sliding problem like this on level ground, coefficient of static friction times gravity is the acceleration you can handle before you start to slide, before anything starts to slide. Michael?
Can you explain again how US mg equals NA?
It's mu, not you.
Mu sub s. Okay, so if this doesn't slide off my hand, if I accelerate it, I need something less expensive.
Here, take this.
If this doesn't slide off my hand when I accelerate, then at every moment that I'm accelerating, it feels a force, right? Or another way to look at it is, by inertia, it wants to stay still. Why is it coming along with my hand? That's because the force due to the acceleration of my hand and the force of friction are equal. Okay? Now at some point, they're equal the whole time. Right? But that doesn't help me find out the maximum acceleration this thing can handle without slippage. To find that out, I got to make it slide. Okay? So I accelerate a little bit more and then it slides, right?
Yeah.
If I know the point right before it starts to slide, right at that point, that's where
Okay.
the maximum acceleration that it can handle without sliding occurs. So that's the right point where the maximum resistance due to friction will also occur. Does that help? I think I could have said it better, but
So that's the. Okay.
well, this, I mean,
I
this,
think
this free body diagram with these two things being equal is true of anything that's not sliding. It's just we keep pushing and pushing and accelerating and accelerating. At some point, this gets bigger and the coffee cups slide. But right at the point before that happens, these two things are still equal. And the coefficient of static friction tells us the maximum amount of an object's weight can use to resist it. So we can set these two things equal at the moment of maximum acceleration are going to be when this thing can only use 24% of its weight to resist the slide, if that makes sense. I don't feel like that was the best thing I could have said, but I hope that helps. Yes?
Did we use these same equations when we did the problem about the train platform yesterday?
Yes. Yes, the train platform and this one. This was meant to be a repeat of the train platform process.
Does seem like it, because it's the whole
Yeah.
friction.
So I'm not giving you like really specific formulas, but these ideas will repeat.
Okay.
It'll happen over and over again. So anytime we're talking about a level ground and how friction helps you keep from sliding while the ground accelerates out from under you, flatbed truck, train platform, coffee cup on a car, you can just say, okay, the maximum acceleration is going to be the coefficient of static friction times gravity. That's a formula you can use.
Yeah, well, and then if you're trying to find the, if you're trying to find mu,
Yes.
you we can just do acceleration divided by gravity.
Yeah, exactly. If I decide to tell you, hey, I accelerate up to this speed, I apply this acceleration, and when I get to this point, an object starts to slide, you can use acceleration and gravity, which you know to find the coefficient of static friction.
Okay.
Any questions on number 14?
Except to B.
We still have to do B and C, right?
No, there is no C.
It's amazing. If only I could read, I could accomplish so much more.
If only I had a brain.
That's exactly right. Okay, I'll leave the free, will this free body diagrams stay for me? What is the smallest amount of time in which the person can accelerate the car from rest to 15 meters per second and still keep the coffee car on the roof?
The coffee
Okay.
car.
Still keep the coffee car, wow, okay. That's not what I meant to say. B. All right, so this question is, what acceleration did we just find?
2.4 meters per second squared.
Excellent. So if you're accelerating, what A tells us is you can go up to you can accelerate at 2.4 meters per second squared for as long as you want, and the coffee cup won't slide. Okay, we're ignoring a lot of things here. In real life, if you accelerate, once you get to a certain velocity, air resistance will knock it off. If you hit a bump on the road, that changes everything too.
It'll just,
But if this car and this coffee cup were on a totally smooth surface in a complete vacuum, you could keep accelerating for as long as you wanted, wouldn't slide, and so.
Wait, what if the car was pretty like a sports car? Like if it was that smooth, wouldn't the coffee cup eventually start sliding?
Well, that's supposed to.
That's not important. Never mind. I'm sorry.
This coefficient of friction is already supposed to take that into account. You know what I mean? Like if it's
it was a stupid question.
No, it's not. That's not. If it's a rough, old vinyl roof of a car or something, then this coefficient of friction will be higher. If it's a really smooth roof, like glass.
Like aerodynamic kind of thing. Or?
I'm thinking no, just the smoothness of the material. All that would matter is is whether it's like a convertible has that rough leather top. A lot of other cars have this smooth. That's all that would matter is the materials between the two. We're not really getting too much depth into that. So basically, if you know this is the most acceleration you can use, what equation do I use to go from 0 to this speed, this acceleration, find out what time it is? Who remembers which
Something
one?
with velocity.
Yes, which one?
V equals V initial plus VT.
Yep. And if you want to wind up at 15 meters per second, starting at 0 meters per second, with an acceleration of 2.4 meters per second squared, what will that time be to 2 sig fig somebody?
6 point.
Jack?
6.4 seconds.
6.4 seconds. That looks about right to my estimation. Everyone get something like that?
Yes.
Yep.
No.
Excellent. We'll talk later. I'm not sure where you cut off the sig figs or not. You can check it later, but 15 divided by 2.4?
No, 6.25.
6.25?
2.5.
Yeah.
I don't think you're supposed to drop the sig figs just yet.
Well, 6.25 would still run to 3, not 4.
True.
Okay, so let's, and that sounds more correct. Okay, 6.3 seconds. All right, so that's number 14. That's basically a review of what we did in October. Shall I go on to number 12?
Okay.
I thought this was the easy one.
You thought 14 was the easy problem?
Yeah.
Okay, right. Interesting.
Means it's not toughed up yet.
Some of them, the theme of this class last year was words are hard. Math's usually not the hard part. It's the word. A 48 kilogram crate is placed on an inclined ramp. We all love our ramps. When the angle the ramp makes with the horizontal is increased, this thing has some ability to move. It's on a hinge of some kind. Oh, that's not a triangle.
Mr. Belville, there's some reminder pop-up on your phone.
Okay, cool. All right. Okay, so, thank you, Jack. This is 26 degrees. 48 kilogram crate is placed on this inclined ramp. When the angle the ramp makes with the horizontal is increased to 26 degrees, the crate begins to slide downward. What is the coefficient of static friction between the crate and the ramp? I gave you guys a shortcut for this. What's the shortcut for finding the coefficient of static friction in this case? Scott, what do you remember?
Never mind, I was thinking of
Okay.
talking about cosine from something else. Never mind.
You remember exactly what it is? Natalie?
Tangent. of
Tangent.
the-
Bingo. The coefficient of static friction between any two materials is the tangent of the angle at which one of the materials starts to slide down a ramp made out of the other two materials. What is the tangent of 26 degrees? I guess it's too soon.
0.49.
Wait. 149.
It just does that sometimes, loses signal. Okay, so we're back. I did this derivation once or twice, Michael, but in brief, at the moment it starts to slide, okay, that's when mg sine theta in this direction and the force due to friction, that's when this just barely begins to overcome this. Okay? So that's when this is equal to, right before this starts to slide, this is equal
They're equal
to,
to each other?
yeah, they're equal to the greatest amount of friction this can, the most friction this box can fight the slide with, if that makes sense.
Still go down.
They'll go down, yes. So what does this mean? This means at this point, mg sine theta is going to equal the coefficient of static friction
mg cosine theta.
times mg cosine theta, because your friction force is always some
Yeah.
percent of your normal force. Okay? Cross that out, cross that out. The coefficient of static friction winds up being sine theta over cosine theta. It's the tangent of the angle at which you start to get slippage.
Tangent of 26 degrees.
Yep, which is 0.49. So that is 12a, right?
Yeah.
Hold on.
So that's your shortcut. If you remember it, you don't have to rederive it on that test.
Why?
But you
Why
just
is
have to
this
draw a
empty?
free body diagram
Why is
anyway.
MG? So on. Why does that have to equal? So friction is the coefficient times mg.
The force of friction is the coefficient of friction times the normal force. The normal force of any object on a ramp is mg cosine theta.
And when coefficient is added, it becomes the friction of the force on a.
It becomes this is the magnitude of this friction vector, of the force of the friction fighting to keep this thing from sliding down the ramp.
I see.
And at the split second before it starts to slide, these two things are equal. And therefore, these two magnitudes are equal. This is one way to sort of understand where coefficient of static friction comes from.
Wait, well, we don't have the. Oh, wait, no, that's your statement. That's
Yep.
just an explanation.
Very good. Okay, so B. 12B. At what angle does the crate begin to slide if its mass is doubled? Well, if we double its mass, I'm glad you asked for this explanation, actually. Whoever asked for this explanation now, I think it was Michael. If you double its mass, this number doubles on both sides of this equation.
But it still doesn't change because it's still.
And it still cancels out, so
Yeah.
B, at what angle does the crate begin to slide if its mass is
So it'll
doubled?
still be 26.
Yep. Still 26 degrees.
Wait, why would it not be like tangent of like 52 or something?
Well, first up, remember, tangent is a transcendental function, Scott. You and I in pre-calculus discussed how everything you know about distributing and order of operations doesn't work with sine, cosine, and tangent. So I should make that assumption anyway with any trigonometric function.
Right.
But the other piece is, remember, the coefficient of static friction is defined as this sort of percentage of the normal force, right?
Oh,
So it's equal to the friction. Look at the mass dropping out on both sides.
yeah.
So I don't care if this is doubled, tripled, quintupled. As long as the ramp doesn't break, this angle won't change, because changing the mass here does the exact same thing here, and we cancel it out of both sides of the equation. The mass is irrelevant. I mean, in real life, there is a point at which the ramp will break, or something else will change. But for now, it drops out, and it's good.
But
So-
isn't it? pardon me, but isn't it still, wouldn't it still be the cosine of the angle itself would be a different? I get why.
If all we change is the mass, no.
Yeah, but when I thought we were changing the, so I'm,
At what angle does the crate begin to slide if
oh,
the
I
mass
see
is
now.
down?
I thought
Okay.
it was angled.
Gotcha.
It reminds
Yes.
me of how in free falling math doesn't matter. I mean, it doesn't matter if you're dropping a 3-pound or 300-pound object, it's going to fall at the same rate.
Correct. As I mentioned before, there are some exceptions to that. It's very because really gravity is a mutual pull between two bodies, but
Yes.
3 and 300 pounds are both basically the same percentage of the Earth's mass, which is almost zero. Okay, the Earth is so massive that 3 and 300 pounds. I mean, if you have one dust mite on your shoulder and another much heavier dust mite on your shoulder, neither one's going to particularly slow you down. Okay, it's if you got an object the size of, I don't know, Rhode Island, it might fall faster than you, but you know, you really have to get to a lot of mass to see a difference. Yes.
Not to disprove you, Stefano, but in challenge this question, what about mass distribution? Like, say it's a jumbo disc, like with literally no weight, but
air-
no, almost no.
Gotcha. Here's the answer to that. The answer to that lies in air resistance, which we're ignoring for now because the math is hard. Air resistance is a factor of really two things: surface area and mass. So if you have two objects of equal mass, you increase one's surface area that it presents to the atmosphere. Air resistance will change for those two objects. But that's a resistant force to gravity. That's not gravity changing, that's just what it does. That's the whole point of a parachute. Take something of very low mass, the fabric, spread it out over a huge area. Air resistance will then help fight gravity.
But the parachute can easily change shape. I'm talking about like a solid, like maybe. Never mind. Forget
Well,
it. I'm getting to hypotheticals.
It's okay. If you put a bowling ball next to a huge disc of similar mass,
It's a free fall.
free fall with enough air, if the atmosphere is thick enough, you'll see a difference. But in a vacuumless room, you won't.
Exactly.
In a vacuum room, vacuum chamber.
But here's another question. When I always say vacuum, I mean I know it means the whole space thing, but what does that truly mean? What is what
let's
is a
talk about-
vacuum exactly?
Let's talk about that later, and
Okay,
not on today.
good.
That's
Good
a
point.
great question for another lecture. I want to
Sad.
take a look at number 10. There's some tricky parts of number 10. I want to see if anybody fell into a trap on this one or not. Okay, it is. To move a large crate across a rough floor, you push on it with a force F at an angle of 21 degrees below the horizontal as shown in the figure. Find the force necessary to start the crate moving, given the mass of the crate is 32 kilograms and the coefficient of static friction between the crate and the floor is 0.57. Definitely going to do this free body diagram. Now, the first thing I'm going to do, let's see, double check what I do up here, but this is going to be the weight of the crate. Is everybody comfortable with that?
Yes.
Okay, then let's give the crate a normal force that's resisting it.
So
That'll be mg on the assumption that the crate is neither levitating nor breaking through the floor. I'm going to save the push for last. Okay, there is some friction here because they say it's a rough floor and they give us a coefficient of friction.
on the left side, or?
I'll put it on the left side for no particular reason. Now, we need to move this down a little bit, I think. And that friction is not yet meant to indicate scale. I don't know the amount of the friction. Okay, I'm not going to put the force of the push in yet. Okay, I'm not going to put the force of the push in directly. So I'm going to use a dotted line to indicate the force of the push. And that's going to be something down here. And we know it's going down at a 21-degree angle, right?
Yep.
Okay.
No, don't use a protractor. We trust
No, I'm
you.
not going to.
Oh,
Don't worry.
good.
Don't worry about that.
Good.
All right, now, here is the horizontal component of the push. Okay, it doesn't just have a horizontal component, though. It also has a vertical component, which I'm going to go ahead and put down here. There's the vertical component of the push, which means, now, horizontal, we should be thinking cosine. Vertical, we should be thinking sine, right? So this is the force of the push times sine 21 degrees. And up here we have the force of the push cosine 21 degrees. Now, does the problem say anything that makes us think that the force of the push is causing the floor to buckle or break?
No.
No.
No? Okay, then the floor must not only be resisting this thing's weight, it must also be resisting the force of this push. So I have to add to the normal force as well. So this will also have a magnitude of the force of the push sine 21 degrees. Do you think this extra addition to the normal force will affect the force of friction?
Why are
No.
you doing that?
No.
Okay.
Sine, cosine.
It has
The
to
force-
resist more.
Though the force of the push is at a 21 degree angle, right? So I'm
Oh,
gonna break it down to its components. Now, so horizontally, Thomas, we've got the force of the push cosine 21, right?
Yeah.
Vertically, we have the force of the push sine 21. That's going into the floor. That means the floor is not just resisting the weight, the floor is also resisting the force of this push. And I think Scott might be about to tell me that this should probably be negative.
Oh,
I want to make
no,
that positive.
but-
That's something you do usually, say that.
I get it.
Okay, yes, what else do you have, Jeff?
I think you were asking about friction. I think it would not affect the friction because I guess it's already getting counteracted. Because the floor, the addition of the weight you're pushing down doesn't really matter because the floor is
Nope.
already.
Got it? Nope. It does. If you push an object like this, friction depends on the normal force. If you push hard, if part of your push goes into the floor, Newton's third law says the floor has to push back up against that. That's part of the normal force. So that
Oh.
will be part of the friction.
And friction is basically.
Yes.
So at the point when it actually starts to move, it's the friction of the push cosine 21 is what again is equal to the friction.
Yes. But the friction is a little different now. Because if I go back here, my normal force, see I didn't put normal force here, I just put mg. My actual normal force in this case is mg plus the force of the push sine 21. My normal force is bigger now. So this has to be part of that. So what we're actually going to wind up with is something like the force of the push in the horizontal direction equals the force of friction at this moment when it starts, right? That's what you just said. But this force of friction is our coefficient of static friction times our normal force, which is mg plus the force of the push.
Sine theta.
Sine theta, yes, which is sine 21 degrees. Yes. Okay, thank you.
But we do know.
So what do we know?
But we do know friction, so you have to.
We'd have the coefficient of friction. Let's see if we know enough. I'm just going to start calling the force of the push F, just to speed up the writing a little bit. You guys okay with that?
Yep.
Yeah.
Okay. And this is going to equal, let's start putting in everything we know. 0.57 is
Yes.
the coefficient of static friction they gave,
Thirty-
times mg 32
Two.
kilograms, 9.8 meters per second squared, plus F sine 21. Can we solve for that unknown?
Wait.
If we can't we eliminate force because
Yeah.
it's in both? Can
No,
we
it's not in every term.
Oh,
we eliminate it by
right.
dividing.
Yeah, otherwise we'll have to divide. We'll have to,
And also,
divide.
we're looking for it. So eliminating is probably strategically less useful.
So
anyway.
maybe we can't.
I got it, yes. We can actually, and for purposes of time, I'm going to show you real quick because we're running out of time a little bit. This will be F cosine 21. I'm going to distribute the 0.57. I'm allowed to do that. So this will be plus 0.57 f sine 21. Then, we're going to run out of room is what I'm going to do.
Then you divide it by 57, right?
Nope.
By 0.57.
Not yet.
Oh.
Actually, that won't help as much as I thought. Give myself a tiny bit more room for the last couple steps here. Then, I'm going to subtract, I'm going to gather all my terms with the force in them on one side by subtracting 0.57 force almost there, guys. 32 kilograms. Double check my algebra. Now, I can factor this force I'm looking for out of these two terms. Correct? Can I do that?
Yes.
Is that a thing I'm allowed to do?
Yes.
I hope so. And that leaves 0.57. Put a parentheses there. So we're almost there. All we need to do is now divide both sides of this equation by everything in these parentheses here. Give me 1 sec.
937.3.
I trust you. Let me show one more step and then...
Oh wait, hold on.
NG.
There we go, 245. That's better.
245 newtons, grams, hectares. What are we talking about?
Newtons, that's the
Okay.
force.
All right. So I hope it should be. All right. So I'm assuming what you did, Nick, is 0.57 times 32 kilograms times 9.8 meters per second squared divided by minus 0.57.
Yes, that's what I did.
Okay. Does anyone else double check Nick yet?
What has he gotten?
245.
Is that getting, are you getting something like that? Not sure if it's right.
It's 250.
Oh, the correct sig figs, it would be approximately 250 newtons. Is it 2 sig fig problem? Yes, it looks like it. So that's the one with the roughest math, actually, I thought was number 10, or the roughest algebra.